Hey guys, welcome back to GoBioEngineering. I am really glad you are here. And if you are new here, welcome. GoBioEngineering is a biomedical engineering learning space where we break down medical technology, clinical engineering, medical devices, healthcare systems, study resources, and career pathways into simple, practical, useful explanations. Before we jump in, do me a quick favor. If this helps you, like the video, share it with another biomedical engineering learner, and subscribe to GoBioEngineering for more explainers and career-focused biomedical engineering content. And if you want the full written article, related resources, and more student guides, everything is waiting for you at GoBioEng.com. All right, let's get into today's article. In this episode, we are going to understand ECG, or electrocardiography, from a biomedical engineering point of view. Where it came from, how the signal is recorded, why 12-lead ECG matters, what can go wrong during acquisition, and how ECG moved from hospital machines to Holter monitors, telemetry, and wearable devices. This guide is for education and career learning only. It is not medical advice, clinical training, or a replacement for professional ECG interpretation. Most people see an ECG as a line on paper or a waveform on a monitor. But for engineers, ECG is much more than a trace. It is a complete measurement system. It connects biology, electrodes, amplifiers, filters, safety, signal processing, user training, and clinical interpretation. An ECG does not show a picture of the heart. It records electrical activity detected at the body's surface. That small difference is important. The heart produces coordinated electrical events. The ECG system measures voltage differences created by those events, then turns them into a readable trace. Before ECG, doctors could listen to heart sounds, feel the pulse, and observe symptoms. But the electrical timing of the heart was almost invisible in routine practice. Scientists in the 18th and 19th centuries learned that nerves and muscles produce electrical effects. Slowly, the heart began to be understood not only as a pump, but also as an electrically coordinated organ. The first challenge was not only finding the signal. The challenge was recording it cleanly. Body surface ECG signals are small. They can be affected by noise, skin contact, movement, muscle activity, mains interference, and the limitations of the instrument. One early figure was Augustus Desiré Waller. In the late 19th century, Waller recorded human cardiac electrical activity using a capillary electrometer. This was a major scientific achievement, but the trace was not yet easy to use clinically. It was slow, distorted, and difficult to interpret compared with modern ECG. This gives students an important lesson. Discovering a biological signal is one thing. Turning it into a reliable clinical device is another. Biomedical engineering often lives in that gap. The person who made ECG clinically powerful was Willem Einthoven. Around 1903, he developed the string galvanometer system, which recorded the heart's electrical activity with much better fidelity. It was not small. It was not simple. It was a delicate laboratory-grade instrument, but it created a trace that physicians could study systematically. Einthoven also gave us the P, Q, R, S, and T naming convention. He helped establish the limb lead concept and what we now call Einthoven's triangle. In 1924, he received the Nobel Prize in Physiology or Medicine for work that made electrocardiography clinically meaningful. For biomedical engineering students, Einthoven's story is beautiful because it shows how physics becomes medicine. A measurement device becomes useful when it is sensitive enough, repeatable enough, safe enough, and connected to a real clinical question. Early ECG helped physicians understand abnormal rhythms, conduction problems, and later myocardial infarction patterns. The ECG became important because it added an objective record. A patient might feel breathless, a pulse might feel irregular, a heart sound might be difficult to interpret. But the ECG gave clinicians a repeatable electrical trace that could be compared over time. Another interesting part of ECG history is telemedicine. In 1906, Einthoven described telecardiograms. Patients were in a hospital several kilometers away, and ECG signals were sent to his laboratory. In simple terms, the heart signal traveled before the ECG machine became small enough to sit everywhere. That idea is still modern. Ambulances can transmit ECGs before a patient reaches hospital. Holter monitors record rhythm during daily life. Wearables can capture a rhythm strip when symptoms happen. The engineering goal is the same: move a trustworthy signal from the body to the person or system that can interpret it. Now let us understand how ECG works in simple terms. Heart cells depolarize and repolarize in an organized sequence. These electrical changes spread through the heart and create voltage differences that can be detected at the skin. ECG electrodes do not inject electricity into the heart. They measure differences in voltage at the body surface. A lead is not just a cable. In ECG language, a lead is a view of the heart's electrical activity. Different leads look at the same cardiac event from different directions. The basic signal chain is heart cells, skin electrodes, lead selection, amplifier, filters, analog to digital conversion or printer, and then clinical interpretation. A normal ECG beat is often described with the P wave, QRS complex, and T wave. The P wave broadly relates to atrial depolarization. The QRS complex relates to ventricular depolarization. The T wave relates to ventricular repolarization. Intervals and segments help clinicians understand timing, conduction, and recovery. But students should be careful not to overclaim. These waves are body surface voltage patterns. They are not a direct movie of mechanical heart movement. Interpretation always depends on the patient, the recording quality, and the lead view. The 12-lead ECG is one of the most important clinical formats. The name can confuse beginners because a routine 12-lead ECG commonly uses 10 physical electrodes: right arm, left leg, right leg, and 6 chest electrodes. The machine then uses electrode combinations and calculated references to create 12 views. A helpful analogy is camera angles. One camera cannot show the whole object. The 12-lead ECG gives clinicians multiple electrical views of the same heart event. This is why lead placement and labeling matter so much. The ECG paper is also part of the interface. Paper speed, gain, grid spacing, calibration pulse, and lead order are not decoration. They make the trace readable and comparable between patients and machines. A common paper speed is 25 millimeters per second. A common gain is 10 millimeters per millivolt. Changing scale or filter settings can change how the ECG appears. Clinically, ECG became everyday medicine because it is fast, non-invasive, relatively low cost, and rich in information. It can help assess arrhythmias, conduction blocks, myocardial infarction patterns, electrolyte-related changes, pacemaker activity, and medication effects. But ECG should not be treated as a standalone answer to every problem. Clinicians interpret it with symptoms, history, examination, blood tests, imaging, and the wider clinical context. For biomedical engineers, that matters. A device produces data, but medicine uses evidence in context. Now let us look inside the ECG machine. The machine has to record very small biological signals in a noisy environment. The patient may move. Muscles may produce electrical activity. Electrodes may dry out. Cables may pick up interference. The device must also keep the patient safe from electrical hazards. The electrodes and gel create a measurement path between the body and the electronics. Poor skin contact can create artifact that looks serious. The instrumentation amplifier boosts small differential signals while rejecting common mode noise. High common mode rejection is central to clean ECG acquisition. Filters reduce baseline wander, muscle noise, and mains interference. But over-filtering can distort clinically important waveform features. Isolation and protection circuits help keep the patient safe. The analog to digital converter turns the analog signal into digital data for display, storage, printing, and algorithmic analysis. This brings us to artifacts. A good ECG engineer respects artifacts. Baseline wander can come from breathing or electrode movement. Muscle tremor can add high-frequency noise. Loose electrodes can create dramatic false patterns. Wrong lead placement can mislead interpretation. Mains interference can appear as regular electrical noise. When an ECG looks strange, ask two questions. Could this be physiology? And could this be acquisition? Good engineering helps clinicians trust the answer. A standard ECG captures a short time window, but many rhythm problems are intermittent. This is why Holter monitoring and ambulatory ECG became important. These systems record heart rhythm over longer periods, while the person continues daily activity. From an engineering point of view, ambulatory ECG adds new constraints: battery life, memory, electrode comfort, motion artifacts, cable straying, waterproofing, event marking, and later data review. The device has to work outside the controlled environment of the clinic. ECG is also part of the story of space medicine and remote monitoring. NASA's Holter Monitor 2 was a commercial ECG monitoring device modified, flight qualified, and used on the International Space Station for human research. Spaceflight made remote physiological monitoring especially important because clinicians could not simply walk into the room and examine the astronaut. The lesson is bigger than space. Modern healthcare uses remote ECG in ambulances, telemetry wards, home monitoring, wearable devices, and cloud-connected health systems. The question is no longer only, what is happening now? It is also, what happened during the patient's real day? Modern wearable ECG brought the technology closer to everyday life. Apple Watch Series 4 or later, and Apple Watch Ultra models, can record an ECG that Apple describes as similar to a single lead or lead-eye ECG. The user keeps the watch on the wrist and touches the digital crown with the opposite hand, completing a measurement path through the body. This is useful because the person may record when symptoms happen. But it is not the same as a hospital 12-lead ECG. It is a limited single-lead recording designed for specific use cases such as rhythm awareness. Skin contact, motion, algorithm limits, regulatory approval, and clinical follow-up all matter. Consumer ECG is still biomedical engineering. The device may look simple, but the fundamentals remain: electrode contact, signal acquisition, filtering, interpretation boundaries, user instructions, data presentation, and escalation when symptoms are important. Digital ECG data is now also used with automated interpretation and machine learning. Algorithms can help with rhythm detection, interval measurement, and pattern recognition. Some research systems look for subtle ECG features that may predict future conditions. Students should be excited, but cautious. AI in ECG is not only a classification problem. Data quality, population bias, false positives, false negatives, explainability, clinical workflow, and responsibility all matter. The future of ECG is not just smaller hardware. It is better context. A useful future ECG device may combine rhythm data with symptoms, activity, sleep, medication timing, oxygen saturation, blood pressure, and clinical records. The engineering challenge is to collect helpful data without creating noise, anxiety, or unnecessary clinical workload. So what should students remember? First, ECG is a measurement of electrical activity at the body surface. It is not a direct picture of the heart. Second, ECG became clinically useful when engineering improved signal fidelity, safety, and repeatability. Third, a lead is a view. A 12-lead ECG gives multiple views of one cardiac electrical event. Fourth, artifacts can look clinical, so acquisition quality matters. Fifth, wearable ECG is useful, but it does not replace a clinical 12-lead ECG or medical assessment. And finally, biomedical engineers should understand both the signal chain and the clinical context. If you are a student, a good beginner project is to use an open ECG dataset and build a notebook that shows the raw signal, filtering, R-peak detection, heart rate calculation, and artifact limitations. The best project is not the fanciest model. It is the one that explains every step honestly. That brings us to the end of this GoBioEngineering audio article. If this helped you understand ECG more clearly as a biomedical engineering system, go ahead and like the video, share it with another biomedical engineering learner, and subscribe to GoBioEngineering for more practical, down-to-earth biomedical engineering content. And do not forget, you can read the full article and explore related study resources, career pathways, experience notes, and student guides at GoBioEng.com. GoBioEngineering covers medical devices, clinical engineering, health technology, radiotherapy systems, biomedical signals, and career routes for students and early career learners. Thanks for listening, and I will see you in the next GoBioEngineering audio article.